Okay, so welcome everyone. We have a special seminar today, and a very great pleasure to have Dimitrios Kantzas with us, coming from France, which this is the institute that I will never be able to pronounce, but it's LAPTH.
Almost, yeah.
Yes, almost exactly. So Dimitrios did his undergrad and master's at the University of Athens. He then moved to the University of Amsterdam, where he is the now world leading expert on hadronic emission processes from X-ray binaries. And now for his first postdoc, he is at that institute. And he'll tell us about X-ray binary and active galactic nuclei jets as cosmic ray accelerators.
Great. Thank you very much. I actually would like to really thank Yanis for hosting me here. And it's a great pleasure. Actually, it's my first time in person in, well, I've been in Heraklion, but not at the university. Yeah, my name is Dimitrios, and I'm a postdoc at LAPTh. Or LAPTh, and it's a theoretical lab in Annecy, which is in France. And I would like to discuss with you how we can mix and merge and try to combine to understand cosmic rays with X-ray binaries, AGM jets, and a tiny bit of dark matter in the very end, if time allows. So without further ado, if that works, I will. Yeah, so what is the main problem I'm trying to address the past few years? We've been detecting cosmic rays. Cosmic rays are charged particles for like decades, over 100 years. And if we collect all the cosmic rays over the years, we can put them all together in one plot. So if we plot the flux as a function of their energy, you can see that there is this super beautiful power law covering more than 10 orders of magnitude in energy, in cosmic ray energy, and more than 10 orders of magnitude in energy flux. And people have been trying to understand where do they come from, how do they accelerate, what is their composition. There are two features in the cosmic ray spectrum. The first one is at energies of around 10 to 15 or 1 PeV. And we believe that cosmic rays from within our Milky Way are accelerated up to this energy with main potential candidate sources being supernova and supernova remnants, etc. And for the most energetic cosmic rays, we believe that they are coming from outside the Milky Way, and the most dominant candidate sources are active galactic nuclei, star-forming galaxies, and perhaps some beyond the standard model theories or more exotic, let's say, physics. But for this talk, I will mainly focus on non-exotic physics. Now, because cosmic rays are charged particles, are difficult to actually detect their origin. So we can use indirect means to understand where do they come from. So imagine, for instance, that there is a bunch of cosmic rays being accelerated in this source here. When these cosmic rays escape, they try to propagate in the Milky Way or in the universe, but because of the magnetic fields, they will be not following straight lines, okay? Now, when these cosmic rays are accelerated in the source, they can interact with other particles or photons, and they will initiate hadronic cascades, and in the very end, they will produce gamma rays and neutrinos. So these gamma rays can propagate the universe, and we collect them here on Earth. Some of them, of course, are absorbed. Neutrinos, on the other hand, are the, as they call, smoking gun, because once we detect high-energy neutrinos, we know that they have been produced by accelerated cosmic rays somewhere out there. So using all these indirect means, namely gamma rays and neutrinos, we can infer more information and understand physics about cosmic rays. By the way, feel free to interrupt me whenever you want. If you want to try to clarify something or repeat, it's perfectly fine with me. So I already talked about two main potential candidates for cosmic ray accelerators. And the first one is active galactic nuclei, just to be on the same page, just to be sure. When I'm talking about AGN, I'm referring to this supermassive black hole that is accreting material from its environment, okay, and produces these two relativistic jets. The jets are relativistic outflows that remain collimated, and they propagate out to kiloparsec distances. And they actually are very good messengers because they transfer energy and material from what's happening very close to the black hole outside out there. And at some point they terminate and they produce these radio lobes, for instance. Now take this and squeeze it to something that actually fits within a galaxy. This is potentially an X-ray binary with a jet. So when I'm talking about black hole X-ray binaries, I'm talking about these stellar mass black holes. So now the black hole in the center has something like 10, 20 times the mass of the sun, is accreting material from the companion star, and occasionally produces two relativistic jets. Now, these jets, of course, they don't carry the same amount of energy, same amount of power as AGN, but still they're very energetic phenomena. For instance, there is a handful of such sources detected in our Milky Way. Perhaps you're familiar with SS43 or Cygnus X1. Both cases have been detected all the way from radio to TV gamma rays. And the jets play a very significant role in this multi-wavelength emission. Now, if you want to understand these jets from the theory point of view, how can we actually try to achieve that? The best way is to run some simulations, okay? We have created GRMH simulations, which stands for General Relativity, Magnetohydrodynamics. So you put all the physical laws that we understand in a box, you solve it, and you try to see what's happening. Or you can use particle in cell simulations, solving fundamental laws between different particles. Here I will play just two short videos. On the left one is the GRMHD, on the right one is the peak simulation. In both videos, you see the number density of particles. And actually here on the bottom left, you can see there is the black hole, and you can see all this material that is expelled. So the blue region here could be something like the jet. On the right-hand side, all the reddish is the accretion disk. And if you look on the right-hand side, you can see that a number density of particles is increasing, is interacting. Super cool and amazing videos. I'm really envy of all these guys being able to show and actually understand, to be honest, all these simulations. But if you want to compare the theory that you extract from this to the multi-wavelength observations, it's impossible, because both cases, they solve different scales. For instance, the GRMHD simulations solve scales of hundreds of RG. So one RG is something like 3 kilometers for the mass, for the solar mass. So imagine when we talk about AGN, that we have like millions or billions of solar masses. Particle in cell simulations, on the other hand, they solve equations and they can track physics that's happening in super tiny boxes. So if you want to compare to simulations, running this to observations, running these simulations takes long enough, so it's impossible. So one way is to step back and try to understand what's happening in these large-scale jets from a semi-analytical point of view. And this is what I've been working on. Building a semi-analytical jet, multi-zone jet model that is capable of reproducing and explaining multi-wavelength observations from radio even to gamma rays. So just to give you an idea of what this jet looks like and what it actually is. Zone model. So imagine that you have a bunch of segments on top of each other, and it can track both the region where actually the jet accelerates and collimates, and then where particles start to accelerate into non-thermal energies. To help you to better visualize this model, imagine that at the jet base, where the jet actually is launched, there is a cylinder of some specific radius, okay? And then there is all these cylinders, and at some point, there is this particle acceleration region. It's actually at the point where the jet has collimated and starts to convert magnetic energy into particle acceleration, okay? And from this point on, particles keep on accelerating into non-thermal energies. Now, we need to understand and keep track of what is the Lorentz factor of this jet. I told you we're talking about relativistic phenomena. And of course, it's very crucial if this jet is pointing at you, what you may have heard as blazar, or if it's pointing 90 degrees, so we see it edge on. Now, let's be honest, we all love to hate, and we all hate that we love magnetic fields. So we need to understand what is a magnetic field in these sources, and a way to visualize that is by the magnetization, which is nothing else than the magnetic field over the rest mass energy. And the rest mass energy, we can connect it to the power that is actually injected in this jet. Now, I talked about the particle acceleration happening at this dissipation region onwards. How do we visualize the particle acceleration? It's actually when, if you plot, for instance, the number of particles as a function of the particle energy, there is a power law from some minimum energy up to some maximum energy, and we need to understand what is the slope of this power law. Okay, we can extract it from either observations or big simulations. Now, to calculate this maximum energy, I can connect it to the acceleration time scale. So how long does it take for particles to accelerate? And why do we need that? Just to remind you, I'm talking about if X-ray binaries and AGN accelerate cosmic rays. So we need to understand up to what energies these sources can accelerate cosmic rays. And to parameterize this, we can do it in this way, by the particle acceleration time scale. Now, here you may see that there is the energy of the cosmic ray, the magnetic field I talked about before, and there is this parameterization F that I will be referring a couple of times in the following slides. So now we have the bigger picture of what does the jet look like. But remember, once we have all these cosmic ray electrons and cosmic ray protons accelerated in the jets, they start to lose energy because of the magnetic field, for instance, synchrotron emission, or when they start interacting with the photon fields, inverse combo scattering, okay? And once the protons start to accelerate, remember what I told you in the beginning, they start to interact with other particles or photons, producing gamma rays and neutrinos. So all these processes are within this jet model. And I can, in that way, understand if and what is the gamma ray emission and the neutrino emission. So I will apply this model in two different families of sources. The first one will be the black hole X-ray binaries, and I will talk about a population study. And then in the very end, I will talk about AGN, and I told you I will try to connect it to dark matter. So let's start with the black hole X-ray binaries. I know that this department is famous for black hole X-ray binaries, but very briefly, just to give you an idea, when I'm talking about black hole X-ray binaries, I don't want to study all of them. I'm mainly interested in actually when they launch jets. And this is what we call the outburst phase, okay? Black hole X-ray binaries, they spend something like 1/10 of their lifetime in this phase. They spend the majority of their life in quiescence, aka boring state, non-flaring state. I will try to understand a bit both, if they can contribute to the cosmic rays. So, the main difference, according to some recent observations, is that in outburst, there is this strong jet compared to quiescence, that there is no jet or there is a very faint one. So that's the comparison I want to discuss on. So in outburst, we have this strong jet. So what I did is take one specific case, Cygnus X1, I named it in the introduction, try to understand what is the entire multi-wavelength spectrum of this specific source, and then try to use a population of 1,000 sources that actually behave like Cygnus X1, which is a high mass X-ray binary, or a GX39-4, which is a low mass X-ray binary, distribute this population in the Milky Way, take a fraction of the cosmic rays from the jets and allow them to propagate and see how they can contribute in the cosmic ray spectrum. So what I'm plotting here is the energy flux of cosmic rays, and this is what we detect actually, as a function of the cosmic ray energy. So if I take the entire population of something like 1,000, remember now I'm talking about 1,000 such sources, and 1/10 of them is high mass X-ray binaries, the contribution must be what I plot here on the blue line, whereas the contribution of the low mass X-ray binaries is what I'm plotting here in orange. Now, there are some uncertainties, and the most important one is actually what I told you in the beginning. The particle acceleration, how we parameterize, because we're not sure what is the maximum cosmic ray energy that these sources can attain. If this scale factor I was referring to is something like 10 to minus 3, which means mildly efficient, or 0.1, which is the most efficient, the spectrum, the cosmic ray spectrum in the GV, in the PV range changes. But what doesn't really change is what's happening in the TV. And you can actually see that perhaps a population of 1,000 black hole X-ray binaries in the Milky Way that accelerates particles inside the jets during outburst can explain something like 50–60% of the cosmic rays in TV. So we still don't answer the question, what are the PV sources, also known as pevatrons, because the contribution in the PV regime is insignificant, but these sources perhaps can really contribute in the TV energies of cosmic rays. Now, I told you that when cosmic rays accelerate, they will produce as well neutrinos. The contribution of these sources in neutrinos will be slightly less, and it's something like here I'm plotting the neutrino spectrum as a function of neutrino energy in TeV, and you can see that it can maximum contribute 5% in the diffuse neutrino emission as IceCube, for instance, in South Pole detects. So this is way less compared to the 50% of the cosmic rays. It's not the dominant sources, black hole X-ray binaries, but perhaps there is still some contribution in this regime. This is what's happening when X-ray binaries are in outburst. So when they produce this strong, let's call it strong jet. But I told you that the majority of their time is in quiescence. There were some recent observations last decade saying that perhaps there is some hint of jets even in quiescence. So what I want to understand now is that if this population of sources in quiescence that we expect to be tens of thousands or even 100,000 sources could contribute something more. What I actually do is take one case, one specific case, one X-ray binary in quiescence, which is this A0620, and I reproduce the multi-wavelength spectrum. So here you can see the flux density of this source as a function of the photon frequency and the different components when particles actually accelerate and produce emission within the jets. One thing perhaps I would like you to remember is that indeed, if cosmic ray electrons accelerate in these jets in quiescence, they can reproduce the radio to X-ray spectra from these sources. Up to date, we don't have any GeV detection, for instance, by Fermi, and doing this analysis, I don't expect any CTA detection as well. Now, having this one source as my prototypical source, I told you I want to understand the entire population. I distribute 120,000 sources in the Milky Way, following one distribution that looks like the pulsars, so a Lorimer line distribution. And this time I try to be a bit more careful with different parameters of these sources, starting by the mass of the black hole, which actually is a scaling factor. So the size of the jet will be different based on different mass of the black hole. And following one specific study by this group, I can derive, let's say, the mass of the black hole for all this population of 120,000 sources. And then each one of these is distributed somewhere in the Milky Way from some distance from the solar system. Okay. Now, if we look on the sky map on the left, we can see all these individual sources, how they look like as a projection on the sky map. Okay. And then if I start comparing different parts with different, for instance, different experiments or in different photon frequencies, here you can see I want to compare what's happening in the galactic center and compare it to what new star detects around this region. So on the right plot, I'm showing the flux as a function of the photon frequency, as new star is detecting around this galactic center. Now, the data are shown here by these diffuse emissions, so all these orange data points. And if I collect each one of the sources that fall on the same region of interest, the contribution of these sources in the diffuse X-ray emission is something like a factor of 5, maximum 10%, which actually depends with the photon energy. And how do I actually rescale how do I know if it's 5 or 10%? It's merely the number of such sources. Because following this population synthesis that says 120,000 black hole X-ray binaries may exist at this moment up there, doesn't necessarily imply that all of them produce a jet. It doesn't necessarily imply that all of these produce a jet with the same power. So you should take this as an upper limit of what is the contribution of quiescent black hole X-ray binaries in the new star diffuse X-ray emission. And I told you, trying to understand different patches of the sky with different instruments, we can find something like 90% by the integral diffuse emission, way less than 0.1% in Fermi bands, which is GeV. In the TeV emission is less than 1% as well. Prediction for CTAO in the future is of the order of 1 plus or minus 1, so might or might not detect something. And in the radio band, it's a few tens of sources to be detected in quiescence. And once more, to be able to better constrain the cosmic ray contribution, we need to also better understand what is the neutrino emission. So once more, I'm plotting the neutrino flux as a function of the neutrino energy. And I compare now the contribution to the diffuse emission as detected by IceCube. But even this observed neutrino emission depends on different models. So even the detection of neutrinos is not super accurate. It has some model dependence. And what you can see is that these quiescent black hole X-ray binaries can contribute up to 1% ish in the 1 TeV neutrino band. Now, the problem is that the TeV neutrinos are dominated by atmospheric background. So it would be really difficult to actually be able to say that TeV neutrinos are coming from specific sources. So the overall picture is that X-ray binaries in flares or in quiescence, they could contribute in the cosmic ray or in the neutrino spectra, but the contribution is not dominant. It's something way less than 1%. And actually, this really depends on different photon frequencies, for instance, or for neutrino energies. But what we have actually been able to achieve is that, yeah, it seems that these jets can accelerate cosmic rays up to some energies. And actually, this is something that also recent observations by Hawk, for instance, or by LASO, which is a TeV observatory, have shown. They have detected TeV emission, and now it's time to better understand individual sources and how actually they contribute in these bands. If I jump now from small scale sources to large scale sources, namely AGN jets, I'm going to discuss something slightly different. So I don't know if there is any urgent question or I. So the idea remains the same. There is this relativistic outflow that accelerates particles. Up to what energy? Let's try to understand, if possible. What I'm doing this time, I'm studying one specific source, Markarian 421, which is a very well-known blazar. If you want to know more, ask Yanis. He has a very extensive work on it, also thanks to polarization. But I will not touch polarization. I'm only interested in the multi-wavelength spectrum. So what you can see here is the spectrum of this source as a function of the photon frequency. And all the observations are from a simultaneous survey of this specific source back in 2009, when this source was actually in a steady state. Something similar to quiescence. But the jet is very well established and very well detected, okay? When electrons accelerate to non-thermal energies, they can produce synchrotron emission that can actually reproduce the entire radio to X-ray spectra. And then when these X-rays are upscattered, they will produce the GV-TeV spectrum as detected. Now, if you want to visualize the jet a little bit compared to what I was talking about in the beginning, the jet base is of the order of 14 gravitational radii, and the acceleration region is located at 30-35 gravitational radii from the black hole. And the scaling factor of the acceleration to be able to reproduce this data is something like 10 to minus 6. So it's not the most efficient particle acceleration, but still enough to be able to reproduce, to accelerate actually cosmic rays to produce TeV emission. Now, in the high energy point of view, what we understand, well, I think I've talked about it many times. Yeah, cosmic rays accelerate and they can produce gamma rays. Great. But if we want to connect it somehow to something more exotic, the idea is the following. When cosmic rays accelerate in the jets, these jets might be embraced by this dark matter halo. So dark matter is like a solution of the cosmological model, and we strongly believe that 20% of the universe is composed by dark matter, but what is the nature of this dark matter? We don't really know. If we want to better understand what's the dark matter nature, and if actually this dark matter can constrain somehow our knowledge on cosmic rays, there is this idea that when cosmic rays start to accelerate in the jets, they start to also interact with dark matter particles. If dark matter is composed by a particle that is of rest mass energy below GeV, and the idea is that cosmic rays boost the dark matter, so the dark matter is becoming relativistic, and on the other hand, cosmic rays lose energy because of these interactions. Now,
Sorry, so
Yeah.
why in the first place you chose Markarian, this Markarian?
the
You knew in advance, I mean, based on its mass, based on the fact that you know that there are jets.
so the idea that the idea that there is a source that is relatively well studied, like Markarian 421, can perhaps give us stronger constraints on both the dark matter and the cosmic rays.
Yeah, but you know in advance that this source fulfills the criteria that you put.
No, I don't know it in advance, and I wish that because we have the entire spectrum, we will be able somehow to constrain the phase space much better compared to if it was some other random blazar with 3 points here, 3 points here. So studying a source that is well understood.
How many other well-studied sources are there?
Yeah, this is true. Many more. But
why,
also-
why specifically this one? This is what I don't understand.
Okay, the idea was also to go a step further and try to understand the polarization as well from the dark matter point of view. But I will not talk about it. I will not touch upon it. But once I have the data of this specific source and I want to understand the polarization, I was like, okay, let's try to understand this part of physics as well. And actually, the fact that we have all these good data points is on our benefit compared to, yeah, as I said, if we didn't have. Now, this is like some hidden information that there is also the polarization that actually we don't use here at all. Yeah, but jumping back to the dark matter, and if it actually a particle, it is distributed around the black hole of the galaxy. But what is this distribution actually? How does it look like? So perhaps you're familiar with the NFW profile, which means that the dark matter is distributed along the radial distance, which will be something here. So here you can see the dark matter density as a function of distance, and this part at kiloparsec distances is the NFW profile. But if you try to connect now the existence of the black hole to the dark matter, and even better, the production of the black hole, because go back a few, I don't know, billion years and think of this premature galaxy with some dark matter around it, and the black hole starts to form. If the black hole starts to form adiabatically, then there are theories that expect the dark matter density close to the black hole to increase and produce something that's called spike. So the plot here shows the dark matter spike very close to the black hole, and further out it follows the NFW profile. Now, we need to be very careful on the normalization of this profile, because actually the idea is the opposite of what usually people try to do. Usually people want dark matter to annihilate, for instance, or decay and vanish and be able to produce gamma rays or neutrinos. Here we want the opposite. We want dark matter to remain in this field and allow us for the cosmic rays actually that accelerate to interact with them. And when I actually try to also better understand the cosmic ray acceleration, because remember, this is my main goal. I want to understand the cosmic ray acceleration. Even if we can say something about dark matter, I want to be able to understand the cosmic rays. So I told you that to be able to produce and calculate actually the maximum cosmic ray energy is by deriving the time scale of this process and compare it to all the losses. So what I'm plotting here is the time scale of different processes, losses, and the acceleration as a function of the cosmic ray energy. And I'm plotting the specific acceleration for this specific factor. So this is the case that reproduces the multi-wavelength spectrum of Markarian 421. Now, if cosmic rays start to get accelerated and interact with the dark matter, I told you that they will start losing energy. But if we compensate with the efficiency of the acceleration, then perhaps we can get energies similar. So namely, here, I'm plotting the dark matter losses, and this time, a more efficient cosmic ray acceleration that in the end will allow for cosmic rays to get up to 10 GeV, similar to what if dark matter didn't exist. So in other words, the dark matter forces the cosmic ray electrons to lose energy, but if the particle acceleration was actually more efficient, they could still achieve energies of the order of GeV. And if I reproduce the spectrum of this case, I plot it here in solid line. So here once more, you have the spectrum as a function of the photon frequency. And you can see in solid line, the case that actually cosmic rays are cooled because of dark matter. And in solid line, the case without dark matter. In terms of jet physics, the scale factor and the size remains the same. So what I want to say from this specific exercise is that if we manage to better understand dark matter with some direct detection, for instance, in some specific detectors, or in other indirect ways, we can better constrain the cosmic ray acceleration, and vice versa. If we had a better understanding for the scaling factor of jets from specifically AGN, we would be able to set stronger constraints on the dark matter nature. Because now this is really degenerate and it's hard to move on. So I think I will stop here, more or less. And what I try to convince you is that black hole X-ray binaries, when they launch jets, they behave in a very similar way to AGN when actually they launch jets. And by coming up with some semi-analytical parameterization, we can capture jet physics and be able to reproduce the entire multi-wavelength spectrum, all the way from radio to TV gamma rays. And with this specific jet model, we have achieved this. Now, in terms of the contribution of X-ray binaries to the non-thermal phenomena, like cosmic rays or the diffuse emission in X-rays or gamma rays or neutrinos, it really depends on different energies, but they will not be dominant no matter what. And the most optimistic case is when actually black holes are in outburst, they can perhaps reproduce something like 50% of the TeV cosmic rays. And in terms of cosmic ray and dark matter, I already told you that if we can better constrain the cosmic ray acceleration, perhaps we can set stronger limits in the dark matter nature and vice versa. If we can somehow set stronger limits in the dark matter, we can refer and we can set stronger limits on the cosmic ray acceleration in AGN jets. So I will stop here and I'm very happy to take any comments or questions.
Thank you very much, Dimitri. Very cool stuff. Do we have questions? people are thinking, and I ask, when you're talking about particle acceleration for over the SD modeling, what is the assumption here? Like, where does acceleration come from? Like shock acceleration, something else?
So that's something connected to the slope, for instance, of the cosmic ray spectrum. Because here, for the case of Markarian 421, I assume that the spectrum is like the cosmic ray population is following some energy dependence to energy to -2. So that implies shock acceleration. And this is also connected to the fact that what is the magnetization or the plasma beta in this specific region. But because I cannot capture the microphysics as peak simulations actually do, I cannot really strongly claim that this is shock acceleration or this is magnetization, because I integrate in larger volumes compared to what peak simulations do. So I remain a bit agnostic on what, if I want to name the particle acceleration phenomenon method.
I'm not, I'm full shocks, but.
Yeah, no, I know.
Okay, so, anybody came up with a question? Don't be shy.
It's more of a comment and thinking out loud
Yeah,
rather than a.
please, yeah.
So I was thinking, that's why I asked at the beginning, why specifically this source?
Yeah.
And how many others do you think that they could help you do what you do now? And the next thought would be, if there are just a few, why don't people already, they haven't done already the same thing with supernova remnants? They're supposed to be the major components of cosmic acceleration, blah, blah, blah. If you ask me, okay, there are not many, but a substantial number of SNRs that emit in TV.
Sure, but the difference now, if the comment is on trying to better understand,
Statistically,
and if trying to better understand cosmic ray dark matter interactions, right?
yeah, more or less, yes.
The thing is that supernova occur in way different regions compared to, now we're talking about a very dense region, very close to the black hole, which is actually the gravitational center of the dark matter halo.
You need the connection between cosmic rays and dark matter, or
Yeah.
just where and why, or from where cosmic rays come from, and then interact with the dark matter.
I want to examine what's happening in the most dense region of dark matter, which is close to the galactic center. Now, if there is a population of sources that accelerates cosmic rays over there, and this is not a galactic, like a jet, that would be great to study this as well. But then we have to somehow be able to understand what is the region, what is the physics of this particle acceleration in this galactic center, if not a jet. And then these cosmic rays start to interact with this dense dark matter material. And supernova occur.
I didn't realize at first that the keyword was dense.
Yeah, that's
from because I just remember your first plot and the knee and the gap in between,
right.
and where that's why.
Yeah. No, this is actually, yeah, this is a keyword. Like now this is the black hole is located somewhere here. So this is the dark matter density on the y-axis, and the x-axis is the distance from the black hole. And you can see that the most dense environment is this one next to the black hole. If there is something else that accelerates actually particles, but super close to the galactic center, then this can be studied as well. But when we talk about extragalactic sources, other sources, it's hard to be able to understand what would accelerate particles in the center. When for Sagittarius A star, for instance, we don't know what produces all this emission. So the idea of the jet is helping a bit because, yeah, we detect the jets and there is the particle acceleration happening. Can this solve this question somehow? Can it contribute to the question?
Okay. Do we have any questions from Zoom? Unmute. One. No, so, okay. So, thank you again very much, Dimitris,
Thank you.
and thank you for